Welcome everyone. So this is our 90th live stream geometry. We have me and 4 other people here with us. And today I'm going to do some more problems from the Geometry Discussions and Problems Discord. So that's a Discord channel that has some absolutely fantastic problems. It's the best source I found, and Stefan pointed it out to me. So thanks for that. So I've been wanting to do the Iranian Geometry Olympiad for a little while, but the problems aren't released yet. So once they're released, I'll do that. But for now, I'll continue with these problems. So if you'd like to join us in the future, feel free to email me at mgreenb801@gmail.com. We do this every Sunday at 8 a.m. U.S. Central Time. And in the U.S., the clocks just shifted back an hour. So just make sure to watch out for that, depending on what country you're in and whether or not you have daylight savings time. All right, so I'm going to share my screen. So here is the first problem. So it's a riddle, so it might be a little bit harder than some of the other ones. So we have a triangle ABC with circumcenter O and orthocenter H. And then we draw the 2 tangents at B and C, and we let them intersect at T. So this is why I thought it might be like a symmedian related problem. Whoops, this is O, H is the orthocenter. So I'll just type it in here, H. All right, let me close it. And let me draw the tangents at B and C. So it would probably be better if I make it a taller triangle so we could see T easier. So let's draw the 2 tangents. And let them intersect at T. It almost looks like, I don't want to make it, well, yeah, I think that's good. So this will be T. And then eventually it's going to ask us to draw the line parallel to BC through T. So we draw this. And then we also draw the tangent to the circle at A. And then we draw the line perpendicular to OH through O. I think that's what it is. Yeah, through O. And we let it intersect. Oops. So it intersects this at Q, and it intersects the other at X. And we want to show that OQ, or 2OQ is equal to OX. So this is Q, and this is X. So yeah, not the simplest configuration, but also not the most complicated, I guess. I feel like overall it's probably a simpler diagram than a lot of riddles. So I'm going to hide and redraw these segments. So we want to show OQ is 2, or is half OX. So 2OQ is equal to OX.
I'm pretty sure we should rewrite, just think of this problem in terms of the tangential triangle. So instead of taking ABC as the main triangle, you just take the triangle formed by the tangents.
Yeah, that's a good idea.
Because H isn't really important, you just get a line OI and perpendicular to that line at O. And yeah, I think it is just much simpler.
So O is the end center, and H.
H is not important. We can practically delete it. you may take the circumcenter and you get line OI practically.
Okay.
Do you understand what I mean?
Not 100% sure. So O is the end center of this triangle, and H.
Yeah. H is not important because you just take the circumcenter of DTE.
Okay.
And that lies on OH. That is like a well-known thing.
Okay.
And it is just easier to work with that. The circumcenter and incenter instead of this orthocenter of that triangle, which is like not main in now. Like.
Okay. So let's see. Okay, so we have the circumcenter, incenter, and the okay, so this is that, is this that like, so it's well known that these three are collinear. Is it like really hard to prove, or it's not that hard?
No, it is not hard to prove at all. You invert around the in circle, and it is quite easy to see that, for example, T would invert to midpoint of BC.
Okay.
And you just have 3 midpoints of AB of triangle ABC. So the circle DTE would invert to 9-point circle of ABC.
Okay.
And you also have that whenever you invert and one circle goes to another, then their centers like stay collinear with the center of inversion. So basically you would have that F, which is the center of circumcircle, and the 9-point center of ABC and O are collinear.
Okay.
And that's it, yeah.
And then, you know, O, the 9-point center, and H are collinear. So then it follows from that. Interesting. All right. Very interesting. So yeah, we could basically get rid of H then. All right. So I'm just gonna make some room here. All right. So I see Leia is rejoining. So yeah, hey Ryan, and hey Leia, she's about to join. All right, so let's see. I think the diagram is going to overlap the problem statement, but that's not too bad. Okay. So we want to show if F is, instead we're looking at the triangle DET, and F is the circumcenter and O is the incenter. And we draw the perpendicular. So yeah, I'll hide H for now, like you mentioned. So yeah, this is kind of like the line IO, and we draw the perpendicular, and we want to show that OQ, 2OQ is OX. And this reminds me a lot of another problem that I did. I think I might have done this problem like once you rephrase it the way that you did. I think I'm not 100% sure. But I think there might have been like a solution using the butterfly theorem or something. Because O is the midpoint of this chord if we extended it. Yeah, I could have sworn there's some problem on my channel with I and O, and then you like take the perpendicular like this. and you show that one thing is twice the other. I could go on my phone and see if I can find this problem earlier on my channel.
I think I have an idea to prove this. Only an idea. I haven't finished it yet.
Okay.
So can you label the midpoint of OX?
Okay.
And let A prime be the antipode of A with respect to O.
Okay.
So maybe if we can prove that GA prime is tangent to the circle, then we will finish the problem.
Okay.
So yeah, we don't need to define point Q anymore. Just let just define point X and G, and then we
Like
can
that.
maybe work on it.
All right. Yeah, I'm gonna check my channel for that problem because see if it's really the same thing or not. Let's see what number it is. Let's see. That must have been a while back. Can't be this far back. Oh, is it video 39? Yeah, I think it's problem 39. Let me see if it's the same idea. Oh yeah. So you take OI, you see where it hits the side, but in the video I had, you see where it intersects the external bisector. So is this this is the external bisector? Yeah. So it reduces to problem 39 on my channel. Yep. And let's see. And basically, yeah, I solved that using the butterfly theorem because so basically, so I drew, here's what it looks like I did. So yeah, it reduces to problem 39 on my channel. Like the new formulation is problem 39. But let's see if I can. So it's like I drew these two segments for these two lines, and then I have this and this, and by the in-center x-center lemma, this is a kite. Because IO is IB is IT and JO is JT is JE. So this is a kite. And then what did I do? So yeah, we want to show that G lies on it. And then is this the butterfly theorem? Because yeah, we have this. So O is going to be the center or the midpoint of this chord. And so, let's see. So if we draw this and we let it intersect here, so this is point Q before, then yeah, by the butterfly theorem, OK is equal to OG. And so that solves the problem, I think. Yes, because this is a kite. So OITJ is a kite, and OG is equal to OK by the butterfly theorem. And so OG is equal to GX is equal to OK, and basically that solves it. All right. So I just used that video from my channel.
That's all.
Or what?
It's a nice solution.
Oh, thanks. All right, so some teamwork there. All right, so yeah, so how did I do that? Yeah, I didn't need a prime for that solution. So yeah, this is looking like maybe the past sessions where we solve the first problem quickly, and then after that it starts to get harder. We'll see. All right. Yeah, those lines, I want to make these two lines a little farther apart. So let me unhide point H, just so when I write up the solution, it's there. So let the tangents at B and C to the circle ABC meet the tangent at A at B and E. All right. Let F be the circumcenter of DET. And then, so F, it's well known that FO and the 9-point center of ABC are collinear. I could say or I'll say by an inversion about ABC, you can prove that.
Michael, I also solve this problem now with inversion.
Oh yeah,
different way than you. Yeah.
Okay.
Just type out your solution, and later I will say what I did.
Okay. Prove that FO and the 9-point center of ABC. I'll say the 9-point center N are collinear. Then O, N, and H are collinear, implies FO and H are collinear. So let DO and at EO meet the circle at I and J. So by the in-center X-center lemma, IO equals IT and JO equals JT. And that means that IOJT is a kite. Let IJ meet QO at G. And then by the butterfly theorem, OQ equals OG. I'll just say OG, or yeah, why not? OQ equals OG, which is half of OX. Since IJOT is a kite. And that it means that 2OQ is equal to OX. All right. So what was your idea with inversion?
So Han already said that you take the antipode of A, and then we want to show that tangent thing, and that is what I did. Okay. So you take the antipode of A with respect to ABC.
All right.
And in order to prove that this is tangent, we want to show that GA prime O is 90 degrees.
Okay.
So also we have that XTO is 90 degrees. That is what we know.
Yes.
So we now will take inversion about the in-circle.
Okay.
And you could just invert points T, X, and G.
About the in-circle. So T goes to the midpoint of BC.
Exactly. X goes to the intersection of the perpendicular from midpoint of BC to OG.
Okay.
So basically it goes to, you take the parallel of Euler line of ABC and yeah, intersect it like that. And G is just a reflection of O and in L. Because G is the midpoint.
The reflection of O over L.
Exactly. So we would now want to show that A prime O is perpendicular to OX because like inversion preserves angles in like the opposite way. So if we want to show that GA prime O is 90, then we want to prove that OG prime A prime is 90.
Okay.
And that basically means that we want to show that A prime G prime is parallel to OH.
Okay.
And now you like take homotopy about O. I mean, it doesn't really matter that we say homotopy. You just want to show that KL bisects OA prime.
KL bisects OA prime.
Yeah, because L is midpoint of OG prime.
Okay.
Yeah, and now you take the midpoint of OA prime.
Whoops, sorry.
Also connect OA, O and A, connect those 2 points.
Okay.
And you see that OA over OM is 2/1.
Yes.
And we basically have the same ratio when we take the centroid, which lies on the Euler line.
Okay, so the centroid would have that same ratio. So the centroid would be somewhere like right here or something.
No, centroid of ABC, it lies on OH.
Oh, of ABC. Yes.
Yeah. So that's basically it.
Okay, because since AO is twice OM, and if you drew this, would it intersect this at the centroid?
Yeah, Euler line.
Because it lies on the Euler line. So AO is 2OM, and this is twice this. And so therefore, OM, it proves that OM is equal to MA prime, which proves that this is perpendicular, and then that solves the problem. Because then A prime G prime O is 90, so which means that G A prime O is 90, which means that that's tangent, so that solves it.
Yeah.
Interesting. I like that. I like how we use the centroid fact there. So it was like, it's kind of interesting. So like my idea used the in-center X-center lemma, and your idea used the fact that the centroid lies on the Euler line, which are like completely different things, but I guess they both end up proving the same thing. It's interesting. Very cool. Thanks for sharing. All right, so I am going to move on to the next problem. Whoops. Did not mean to do that. Let's try this. All right, so we have a triangle, and then we draw the 3 altitudes. There we go. So even this, I felt like looked a little bit similar to something from before. So we have AD, BE, and CF, and they meet at the orthocenter. Let's see, D, E, F, and this is H. X lies on EF such that HX is parallel to BC. So I feel like I've seen problems with the perpendicular bisector of HB, but I'm not sure if I've just seen it like this, or it's just like the parallel through H to BC. So this is point X. And XD intersects AB at L. So this is L, and Z lies on BC such that LH is perpendicular to LZ. So we draw the perpendicular to this. And we want to show that LB is equal to LZ. Interesting. So basically, yeah, that we have an isosceles triangle there. So that seems like it should be equivalent to some angle condition, right? So hide a couple things. And then this is like a right angle right there. Let's see. Looks pretty good. So this is a cyclic quadrilateral. And so this angle is equal to this angle. So it's kind of like we want to show BLD and HLD have the same circumcircle, or the same size of their circumcircle. Let's see. And then this angle is obviously 90 minus this angle. And HX is tangent to this. I don't know if that helps. All right.
Isn't that just the same as saying that HX bisect angle FHL? The problem is equivalent to that, right?
Is that, did you get that like from an angle chase or?
Yeah, so we need that
Apollonius circle, right? Apollonius circle.
Okay. So angle FHX is angle BAB. And
90 degree minus angle B.
Which is 90 minus B. Yeah, okay. So yeah, it's equivalent. It's equivalent to showing that this is the angle bisector. I see what you're saying. All right.
Oh, this one isn't hard. We can use harmonics.
I was just thinking that. Okay.
Wait, did we just solve the problem at the same time?
Yeah, we really did.
My solution is to project through F onto AC.
Okay. Okay, so project through F onto AC. Do we project it like these?
So look, you have that XHD is 90 degrees. And we have we want to show this angle bisector thing. So if you intersect XD and the CH, you should get a harmonic bundle with points XL and D at that intersection.
Okay.
That is what we need to prove.
Yes.
And you project that cross ratio through F onto AC, and that's basically it.
Okay. So that would be A onto AC. So D, we would intersect FD with AC, right? But then that's obviously one because yeah, by harmonics, because these concur. So
was your solution different, Khan?
I also use a cross ratio and projecting, but I project onto AD. Yeah, that's it. It's just the same thing.
Yeah, it is the same. Okay.
I'm just going to say like the cross ratio HF, HX, HL, HD. And then, well, okay, so, oh no, we do, yeah, we do want to draw that. Okay, so, all right, let me just make some room. Something like that. I think that looks good. So yeah, there's a couple more riddles after this, so try those. Okay, so let CF intersect DL at G. Yeah, sorry, my boss keeps texting me. He's like distracting me. He wants me to do something after the session's over, even though it's the weekend. All right. So let CF intersect DL at G and let DF intersect AC at I. All right. And then, so we're going to try to show that GXLD is harmonic. So we can project through F. GLXD, that should be equal to CAEI. -1. So since angle HXD is 90, then that means HX bisects angle GHL. right. And once we know that, then it's not too hard to show by an angle chase, because this angle, it's 90 minus this angle, which is 90 minus this angle. Well, we could just say angle LHT is angle FHA, which is angle, yeah. So we have angle LZB is LHT. Which is angle FHA, which is angle ABD. And that means that LB is equal to LZ. Angle LZB is angle ABD, so that's isosceles. All right, so I'll move on to the next one. So yeah, this one was a little bit easier. You just project and then it solves it pretty quickly. So here's another middle riddle. Let me try a riddle. So this one uses isogonal conjugates, but it's not that long of a problem statement. So we have a triangle. Again, we have like the Euler line show up. So let's draw the center. All right, and X lies on OH, and then we draw the isogonal conjugate of X. So this is X. We're going to end up drawing the pedal circle of Y, which is the same as the pedal circle of X, so we might as well just draw right now. So O and X have the same pedal circle. They're isogonal conjugates. So this will be this pedal circle of both X and Y. In fact, what I could do is I could just take the center of this circle and reflect X over it, and then that's Y. So that's Y. We want to draw the pedal triangle of Y. And G is the centroid of that. So I'm going to rename this G as something else. Let's call it K. And I'm going to hide these. Okay. And basically we draw the centroid. So G is the centroid of Fij. Is the centroid triangle center 1? I think it is, right? Fij1 looks like it. We want to show H, Y. They don't look collinear there. So I don't know. Oh no, 1 I think is the in-center. I think 1 is the in-center. What's 2? I think 2 is the centroid. Yeah. Okay. They're so close together. It's maybe if I make it like a tall triangle, it'll be easier to see. They don't look collinear there. Is that the centroid? Let's see. Maybe I did something wrong.
Wait, same thing went wrong for me. My diagram isn't right. I don't know if it happens to other people too.
So maybe the problem is wrong.
Problem is true.
Oh, it's
My
true.
diagram looks true.
X.
You took.
M. Yeah, what did I do wrong here? So X and Y are isogonal conjugates. G is the centroid of the pedal triangle. You're seeing that the diagram, you're seeing that the problem's true when you look at it, right?
Yeah.
Let's see. So let's check that X and Y are actually isogonal conjugates. It looks like it. ACX and YCB. Yep, so they are isogonal conjugates. O is the circumcenter. H looks like.
Oh, yeah, never mind. I thought you drew something wrong, but no.
Okay.
I see actually what you did wrong.
Okay.
You took F as the perpendicular from Y, which is not.
Okay. So. Okay, so F is wrong. Well, F should be the perpendicular from Y to BC, right? Oh no, it's like no, you're right. So this is not. Let's see. So F is the perpendicular from X. I need the other point. There we go. Let me call it N instead of M. N. Yeah, F and N are so close. If I make it more like an obtuse triangle, they get farther away, but then O and H get really far apart. So I guess this is probably good enough for now. So so whoops. We want I, J, and N. Keeps doing F. I'm going to delete L. And then now I'm going to define G again. So G, that's I, J, and 2. And now they look collinear. All right. Although Y and G are really, really close. So let's see. If I make it a tall triangle, does that help? No, then they get even closer. Yeah, Y and G are really, really close. I could try, if I make it like an obtuse triangle, then they're farther apart, although I don't know if I want to make it an obtuse triangle. Yeah, the only way to really make y and g farther away, I think, is to make it obtuse. Otherwise, they're very close. I can move x. Oh, good point. I should have just done, yeah. Thanks, Ryan. Yeah. Okay. Let's make, there we go. I like that. One sec, guys, I'll be right back. All right, thanks for waiting. So yeah, I don't know if it's worth drawing this segment right here. So basically for any point that's the isogonal conjugate of something on OH, then H, Y, and G are collinear. I wonder if we can state it in the reverse. So we could draw, well, yeah, I don't know if it would be that easy to state it like that. Obviously, angle XAO is HAY. Yeah, I wonder if there's any like packet on isogonal conjugates that has like more than just the basic theorems. So Stefan, I know you asked for a packet on the line OI. I feel like I might have seen that a long time ago, but yeah, I just couldn't find it. But maybe there's something like that for isogonal conjugates. So the 9-point circle is the pedal circle of O and H. What can we say about the pedal circle of a point on the segment OH? So yeah, if we drop perpendiculars from H and O, then they're like I and D are symmetric about the midpoint of that segment. And same with F and N and same with E and J. So maybe it's worth drawing, it's probably worth drawing the 9-point circle. So I'll do that. Although it might be close to these points, but oh. So yeah, if we draw the 9-point circle, we get like a symmetry. If we draw these like other points. All right. So it looks like Johannes just joined. So thanks, Johannes. So we're on our third problem here. We saw the first two pretty fast. But this one is a little bit harder, I think. So what would, where's the point right here that I'm missing? Let's see. So be like this point. So yeah, we have a certain symmetry where it's like, wait, it doesn't look like, let's see. Oh, because K is not the 9-point center. So, okay, maybe it's not that helpful then. It's like I was thinking that dP is IQ, but that's not true. Yeah, I'm gonna erase the 9-point circle for now. It's not as good as I thought.
Isn't the isogonal conjugate of the Euler line some triangle cubic? Some important triangle cubic?
So a cubic?
Yeah.
No, isogonal conjugate of Euler line is hyperbola.
Oh.
I just looked that up 5 minutes ago. I don't know why, but we may assume that right now.
Interesting. I didn't know that. It's a hyperbola.
I saw that it is called Yarabek hyperbola or something like that.
Is any line, do you know if for any line the isogonal conjugate's the hyperbola?
I think it is not. That it is just some very special thing and it is quite chaotic in most
Okay.
cases.
Does it
That's
have
fair.
any interesting properties? This hyperbola?
I don't know really. You can search it up.
All right. Interesting. Jarabek hyperbola. Let's see.
The thing that it is hyperbola in some cases can be useful just because you can project cross ratios in conics generally. I've seen it one time
You can
for one proof.
You can project cross ratios onto a hyperbola.
Yeah, just like you do on circles and stuff.
Any conic.
Yeah.
That's pretty cool. I knew you could do it on any conic, but yeah, I've never actually seen it like in a solution to an Olympiad problem. But that's interesting.
I saw that in I3435, one of his blogs, where he proved some collinearities of.
Oh, was that the
point.
problem with like the feet of the angle bisectors? And then he showed that like the orthocenter of that triangle and
No,
what? No,
it isn't
not
that.
that. Different one. So I think he might have used conics for that problem too, but I'm not sure. So we want to show, so we have X and Y. Maybe we could show HK. Okay, we know HK is a median in triangle XHY.
Sorry, what is K?
K is the midpoint of XY, and it's also the center of the circle. So yeah, X and Y are isogonal conjugates, and the midpoint of XY is always the center of the circle that goes through like the feet of the altitudes from X and Y.
Oh, that's cool.
Yeah. And yeah, of course, the definition of isogonal conjugate, we have angle XAC is angle YAB, and then XCA is YCB, and so on. XBA is YBC. So yeah, we know XK is the median of this. I don't think, I would be very surprised if OG was parallel to XY. Let's see. Yeah, it's not. At least I don't think so. Oh, Ryan is thinking about using moving points. So maybe we could just show it for 3 points. Like, yeah, is it obvious when X equals O? So if X equals O, it's kind of tricky because you'd have to do like a limiting argument. Like you'd have to show as X approaches O, then Y approaches the line HG. I'm not sure, but maybe for a different choice
Maybe
of
it is
X.
just obvious because H and Y would be the same.
Yeah, but I think like I don't know if you can just use that, like, because there's an infinite number of points if it through, like I think you have to use that as X approaches O, that Y. Yeah, like I don't know. Can you just say it's trivial like that? I don't know.
I don't know. If we could say, then it is trivial for O and H, and probably we can do something for 9-point center.
For the 9-point center. So yeah, for the 9-point center, the isogonal conjugate of the 9-point center is the cosmeta point, right? So let's see, Ryan. Complex coordinates. Now, you all know that I prefer synthetic solutions, but is there a good way to do complex numbers with isogonal conjugates? Okay, so yeah, Ryan was saying we could maybe use projective transformations. I think another problem. Okay.
Just wait a bit. I want to hear the projected transformations.
All right. But yeah, like I feel like there's so many of these orthogonal conjugate problems that we've gotten stuck on. And I feel like there must be some more lemmas that can give a synthetic solution. Like there has to be some other lemmas on it.
Do we know anything about the locus of G?
The
Yes.
locus of G.
If we want to do like moving points, we would need to know something about it, right?
Let's see. So G, I'm not sure what curve it traces out, or if it's anything. Yeah, I don't know if this is like a hyperbola or something. I'm not sure. So yeah, we could spend another 5 minutes on it. And then, yeah, I could switch to another problem. Oh, so yeah, Y traces out the Jerabek hyperbola. Yeah, G, I don't know exactly what that would be.
G looks like a hyperbola.
Oh, really?
Looks like. Not sure.
Interesting. So yeah, let's see what the Jerabek hyperbola looks like. So I'll move X around and then Y.
You can
That
use
should
a conic tool in GeoGebra.
There should also be a tool for the locus now.
You could use the conic tool.
Conic through 5 points, and you take A, B, C, O, and H.
Okay. Ah, that's cool. Interesting.
Does any of you guys know how to use complex coordinates?
I am not.
I know a bit. I know a bit, but it looks a bit tricky to compute Y. I mean, we don't really need Y, but those pedal points.
So for the moving points idea, is it necessarily true if we have 2 points with degree 1 that some weighted average is also degree 1 or degree 2 maybe?
I'm not sure. I don't know moving points that well, unfortunately. Ryan, I think maybe was saying that if you have it, if you know it for 3 points, then you can prove it in general. So maybe if we could prove it when x is O, H, and the 9-point center, that might do it. But I'm not sure.
You need to show that there's a projective transformation taking x to g. So taking the Euler line to the locus of g, that takes x to g at every point.
Okay. It takes x to g.
Or y to g or something. Because the point is that if we know a projective transformation on 3 points, we know it everywhere. So we construct 2 different transformations, and if the problem is true in 3 points, then these transformations are the same transformation in 3 points, so they're always the same, and then the problem is true. But we can't just do that without knowing anything about those transformations.
Okay.
Or alternatively, we can compute like degrees of points if we take their coordinates to be like polynomials of some parameter.
So that kind of tells you how many points you need to check it. So you need to check, like,
Exactly.
yeah. All right, I think I'm going to move on to another problem for now, but we can come back to this later if we have time and end. So yeah, Johannes, so yeah, this problem we saw really fast. This one was a fun one. And I actually used a different problem on my channel, and then Stefan found another solution. Let's see. So this is a riddle. Let's try another riddle. This one looks kind of hard actually. So I'm gonna try this one. So we have like a 60-degree triangle, and I is the in-center. So what's the best way to draw 60 degrees? So usually I do it like this. I don't know if this is like the best way to do it, but it works. So that's obviously a 60-degree angle.
There should be a tool. The fourth one from the right should angle with given size. Then you can just say 60 degrees.
Yeah. So yeah, I guess it's probably best, yeah, to do it like this. Oh, whoops. It's like point, vertex, and 60. Oh, I want to do it the other way. So this point, oh, it's the other way. Okay, so, sorry. Point. What about this whole ray? That's really what I wanted. Then this vertex. Oh, I think it has to be a point, not a ray. I think that's why I was getting confused. Okay. And this is AB. Let's make C some point on this ray. Yeah, that should be good enough. So yeah, now I can drag B and C as far short as I want. I is the in-center. And BI and CI are the feet of the angle bisectors. So let's see how I can do this. I go like that. Like that. All right, so let's draw the in circle. And I is the in center. And then we'll draw the feed the angle bisectors. E and F. So, whoops. Let's see, I might have to zoom out. Yeah, let me make it more like obtuse, or maybe just bigger, so that it'll do it. See if that helps. There we go. I'm gonna have to rename it, but so this is E and this is F. And then we want BEPF and ECFQ. So F is that parallel, and this parallel. That'll be point P. And then ECFQ, this and that. All right, so we have this point and this point. This is P, and this is Q. And X is the in-center of BIC. So it's like the in-center of a triangle with the in-center. So, and then, let's see what it called that circle, D.
We
So
can
X,
we can calculate angle BXC in terms of BIC, so maybe we don't have to.
Yeah,
just keep it.
I agree. We don't even really need. Yeah, we don't even really need X.
It should be 150 degrees, but now when I look at the picture, PAQ doesn't look like 150.
Let's see.
Actually, what is BIC? Is it 120 degrees?
Yeah, I think. Let me check. So this is riddle 264. Let me check the chat. Wait, did you just say I don't want to do any? Okay, IGEO 2019, but wait, riddle 264. Let's see.
Oh, now I see. We need to prove that BXC is less than PAQ.
Oh, is that what riddle 264 says?
Yeah.
Oh, I don't like inequalities. Let's see.
Same for me.
Oh, it's less than. It's not equal to. Okay, let's do one that's not an inequality. This one is kind of hard.